Hello, welcome to our video presentation of Developing Mathematical Minds. With today's link, there also should be a link to the 3 handouts that we're going to be using and I will reference. So if you haven't had a chance to print those out, if you could. I'm also going to ask you to pause the video 3 times today, so please get familiar with your pause button. And the first time I want you to pause actually is right now. I want you to read our mission statement if you haven't. To me, it encapsulates joy of learning. I see my job as working with the classroom teachers to make sure we develop students who are creative and critical thinkers, who are expert communicators and collaborators and passionate about what they learn. So part of developing this passion means math is a really active place, sometimes a little bit noisy. So I'm going to take you behind the scenes and show you some pictures I took in the first 3 weeks of math in the lower school. These aren't any special lessons. They're times I wasn't teaching and had my camera with me. So this here is a first grade math class. Down at the bottom you see students playing number line hop and card top it. We are always talking math to learn math. In the upper left corner, you see Chrissy Orsini is doing a quick assessment. She's having students count out collections on 10-frame mats. Let me show you what a 10-frame is. This is a 10-frame map that loops 10 ones into 110, and she's specifically doing this to overcome some deficiencies of the English language. It's really hard to learn place value in English. Our language is irregular. The first counting words up to 30, there's no discernible pattern, and our numbers are encoded. Here's what I mean. When I went to Japan and I was learning how to count, when I learned 16, I was literally saying 110 6. When I was saying 26, I was saying 210 6. So 20 was explicit. It was always 2 10s, 6 ones. 30 would be 3 10s, 6 ones. To add insult to injury, in English, our teen words are said backwards, the syllables. So think of a 4 or 5-year-old wants to spell cat, and you say, oh, honey, sound it out and write down what you hear. Cat, C-A-T. 16. Ooh, we say the 6 before the 10. But don't write 61, even though that's what you hear, 16. So our language has some deficiencies that we want to overcome with visual models, so we use 10 frames. So what about a first grader who already understands place value? Well, so for them, instead of having them count out the 26 dimes, we might say, what is the value of the 26 dimes? If they already know that, we might instead have them work with quarters, and we say, terrific, you see 28 quarters, what's the value? How close are you to $10? So math is something, a topic we can always go deeper on, and we can always have students working at multiple levels while we're building a concept. Over in the right corner, you see Dr. Marcy, the classroom assistant, who is doing a weekly store, and we purposely have students work once a week with pennies, nickels, dimes, and quarters, because to compute fluently in our base 10 number system, working with 1s, 5s, 10s, and 25s is really helpful. So we're building that early on. This here is the second grade class. Again, we use coins, and here is the first week of school. The mathematicians in the upper left corner are counting their coin collections to figure out how much moolah they brought in. On the right, students are playing a dice game. They are working on a hundreds chart, developing place value understandings. Down here we have a student counting by 7s, developing her early multiplication number sense. And this picture here, again, the girls are playing the place value game, but what I want to bring your attention to the mathematicians behind, who have finished the game and they're going into their puzzle packets. And in first, second, third, and fourth grade, every student has a puzzle packet. And in there are packets for them to work on. It might be numbers and operations, spatial reasoning, measurement. It's individualized, and the point I want to make to you is that there is no downtime or idle time in a math class. When a student finishes their work, they immediately go into their puzzle packets. This here is math spilling out into the hallway. You can see our second graders are graphing how many different shapes they've used in their design. They've got so many circles that they're having to label the counting by 10 numbers to figure it out. Over here we have a second grader who is putting up equations she and her classmates have created. She's creating a hallway display. The teacher was assessing the student's understanding of the equal sign. Are they viewing it only operationally? It means the answer is coming. Or are they seeing it relationally? That equal means the same as. 20 minus 8 is the same as 11 plus 1 because they both are expressions of 12. This whole concept of equivalence is developed very purposely in the lower school, and you're going to see it throughout this presentation. This here is a third grade class. Up at the top, we have students, I think this is the second day of school, who are working in partnership. So you see two girls here on the floor working together, and here you see the classroom teacher setting up a student who's in school with a student who is quarantined at home, who's over here on the iPad. And I've included this just because I want to give a shout out to my teacher colleagues who are doing a phenomenal job to make sure no matter where your child is, whether they're in the classroom or they are at home, that they are part of a cohesive classroom community learning together. The bottom two pictures just charm me. The recess bell had rung, but these mathematicians were hard at work. They were still around the room measuring the perimeter of different objects, whether it was the couch or the Billy Bongs cage there. The teacher is assessing whether or not these third graders have a reliable method for multi-digit addition, and they're generating their own add-ins by finding items to measure the perimeter. These, if you're in third grade, you've probably heard about special math. This happens every Thursday, and students either go into Paula DeWitt's room or Nan Conroy's room for a special math class. Here they're learning how the coordinate plane works, which, as you know, is the basis of your car GPA, or the GPS on your phone. To the right, they're doing spatial reasoning puzzles with toothpicks. Second grade parents, you got a little taste of this with a recent homework. It's a lot of fun. Here we've got fourth graders trying to find the average fourth grader. They have done a data collection, and boy, I could spend a whole hour on this. In this century, we really want to make sure your students are literate in measures of central tendency, that they are honest purveyors of data, and that they are wise consumers. So here they are finding out how many books do their classmates read a month, how much time do people spend outside, how much time do fourth graders spend on electronics, how many years have they been at Key, how many pets do they have, how many siblings. All of that information is being put together. Bottom right, you can see they are lining up their data from small to large to find the median value. And the final picture here is of a fourth grade classroom. Again, they're on the floor working in partnerships. They're on the board figuring out their computation. But what I love here is students are at the desk, but the teacher is on the floor. So you've seen some of these pictures that our teachers are all over the place working in small groups with your children. In this presentation, I'm going to focus mostly on numbers and operations, but we do make sure we do achieve all of the strands. Our math curriculum is developed through the national standards of teaching for mathematics. Our goal is to meet and exceed every standard at every grade level. The biggest difference between your child's education now and, at least for me when I went to school, is students have to understand conceptually every procedure they use. So here is a fourth grader who is showing her mastery of long division, and she's checking her work not by dividing again, but she's taking her quotient, 718, she's multiplying it back by her divisor, 5, adding in her remainder, and getting her initial dividend. And there she is. She's like, bam, it all worked. How do we do this? How do we develop mathematical minds? It's very much like building a house. So I'm going to use this analogy. When you build a house, you want a really strong foundation. So we make sure your child's basement is wide and deep, and in there are systems that are going to run throughout the house. So you might have your electrical, you might have your heating, your air conditioning, and your water, your plumbing. Those are systems that go throughout your house, the way number sense, place value estimation, and the language of math, or the symbols that we use, go throughout the house. But you don't just do the basement. As you are building your basement, you're also framing out the walls of your house, right? And putting the roof on. And so we start problem solving from the get-go so that your child has opportunities to develop judgment and self-monitoring and analysis. So let me talk a little bit about number sense and place value. These are some keywords, and one of your handouts has this model and has definitions of the words that I'm going to be using for you to refer to. So number sense. You've got this problem to solve, so if you could just pause, that's on the other handout. Pause the video and go ahead and solve this for us. And many of you have probably solved it this way with a tried and true subtraction algorithm that you've used. This is a beautiful method. It actually democratized the marketplace in the Middle Ages in Europe, so I'm a real fan of this method. And I know some of our parents also thought about this problem a little bit differently. They went, well, if I just add 5 to 2,995, I get 3,000. So I can jump back 3,000 and then add 5. This would be computation with number sense. Both methods are good. Mathematicians use different methods, actually, depending on the mood they're in. I think I might have told you about a study where a group of 1,000 mathematicians were at a conference and they were given a subtraction problem to solve, and they all solved it. And the next day they were given the exact same problem to solve, and most of them, 90%, solved it a different way because they saw different number relationships. They were in a different mood. Place value. This is really a beautiful thing. So in our base 10 place value system, as you know, we group things by tens. We group 10 ones to make a 10, 10 tens to make 100, 10 hundreds to make 1,000, and so forth. Place value has been invented 4 times in human history. The Babylonians with a base 60 place value system, the Chinese with a base 10 number system, the Mayans with a base 20 number system, and then most recently in India, another base 10 number system created separately from the Chinese. So it's pretty interesting. It's come up 2 times with base 10. That is the Hindu-Arabic number system that I'm using today. In it, we would read this number as 31 million. Often you'll see our students are labeling the numeric period, the comma underneath, with the name of the numeric period. So 31,078,006, and you can see 0, which is invented twice by humans, is a really important placeholder in a place value number system. To really gauge a student, or to help students understand place value, we sometimes contrast it to a number system that's additive. Our second graders learn Roman numerals, which is a lot of fun, and they think they're learning a code, but really we're doing it to help them see the difference between a place value system and an additive system. So we have just 3, takes 1 symbol, base 10 blocks, 3 blocks, Roman numerals, I. 33, pretty easy to do in Hindu-Arabic, just takes 2 symbols, but now I'm doing 6 pictures and 6 characters here. 10, 10, 10, 1, 1, 1. 336. Now the children are getting a little bit tired because it's a lot to draw, and in Roman numerals it's a lot to write. And then they're like, oh, we see where this is coming, and we go, no, you just have to do 1,000. So 1,333, they do 1,000 block, 300s, 3 10s, 3 1s. And again, in Roman numerals, the M for 1,000, the 3 C's for 100, 100, 100, so it's additive. 10, 10, 10, again, additive, 1, 1, 1. And all of a sudden, they see the efficiency of a place value system where the digit is placed, the position tells you how many groups of tens, hundreds, ones, or thousands. We can really understand we can gauge a student's understanding of place value when we go to the right and go into decimals. And so we would read this. We don't in the lower school say point. They'll start using that in science in 5th and 6th grade when they've got 5 decimals. We read this as 9 and 900ths, 9 and 88 thousandths. You say the name of the last place value position, so which is greater? And this mathematician here, let's look at this one here, is saying 9 and 900ths is greater. 9 and 900ths has 9 in the hundredths place, whereas 9 and 88 thousandths has 8 in the hundredths place. So he is comparing like positions. He is comparing the 9 here in the thousandths place with the 8 here in the thousandths place. His classmate is taking a different approach. And she says, I made the denominators the same. So you see here she put a 0, so she made this 9 and 90 thousandths, which she knows is greater than 9 and 88 thousandths, or 40 hundredths is greater than 4 hundredths. So she knows decimals are just fractions with the denominator of 10, 100, or 1,000. All right, I would like you to take a minute to try out the 4th grade math problem. You can go ahead and cut out some number tiles, or you can just use the numbers 1 through 9. This is a 4th grade math problem that they do at the beginning of school, the first week. We do tell the children that it takes more than one period. Often it can take 45 minutes, 90 minutes to solve, because we want to help them manage their frustration. It says use the numerals 1 through 9 to form two 3-digit addends that make a 3-digit sum. So you're only using 1 through 9. So if you could hit the pause button and give this a try. All right, welcome back. Hopefully you paused and gave it a try. And in the classroom, and after about 10-15 minutes, students start sharing their strategies, and we start putting solutions up on the board like this. And then the students start to notice teachers are putting some on the right and some on their left. And the question is, what are the solution categories? And we start to analyze it. And you can see with the ones here on the left that the ones column, the 4 and the 8 have made a 12, so we have regrouped a 10. The 9 and the 8 has made a 17, so we've regrouped a 10. Over here, we're regrouping 10s to 100s. So here, 1s to 10s, but 10s to 100s on this side. So then the students go, would a solution work with 2 regroupings, where we regroup 1s to 10s, 10s to 100s, and they go back to work? Nope, found out that doesn't work. Then we look at some other questions. Oh, what do you notice about the sums? All right, I'm not going to answer that. I'm going to have you look at that and see if you can see some similarities in all the sums of these problems. We absolutely ask is, if instead of having a plus sign here, we had a minus sign, would that be possible? And the students want to run back to their table and work with their tiles, but we say, wait, just think for a second. And then all of a sudden, a student will say, you know, I know 3 plus 6 is 9, which means 9 minus 3 is 6, or 9 minus 6 is 3. They know the inverse operation, so I can just take my sum here and make that my top minuend. And I can subtract one of my addends, and I will get the other addend. So yes, this problem is absolutely possible with subtraction, because subtraction is the inverse operation to addition. Well, how do our 4th graders know that? Well, they've been looking at fact families since 1st grade. So this is their work a couple years earlier, where they're showing the relationship between addition and subtraction, as well as look at the placement of the equal sign here and here. They're beginning to see equal just means equivalence. Strategies for number facts. This is a big part of your students' foundation. How we build understanding of number facts develops their fluency in our base 10 number system. I'm going to give you just a couple examples. We work on doubles facts. If a student knows 6 plus 6 is 12, then they easily know 6 plus 7 is 13. So we build doubles and near doubles. If they know 10 and 6 is 16, then they know 9 and 6 is 1 less, it's 15, and they have lots of strategies for that. We work diligently on developing fluency with 10 partners, and immediately then, once they have these number combinations under their belt, applying it to 20s partners, 100s partners, and here you'll quickly see a 4th grader who is doing a subtraction problem using an algorithm. Terrific. And here another student is doing the exact same subtraction problem and just applying 10s partners, going, well, I know if I have a 0 up top here and I'm adding from 3 to something to make it a 10, I have to have a 7. And then from that, they're actually then doing 9s partners. They are mentally doing this, by the way, applying 10s partners to their subtraction. We use doubles a lot. This is a 2nd grade story that we read, and we are building on students' knowledge of doubles facts. In the story, Jack has some magic seeds, and they keep him full for a year if he eats one. So in this story, he's got 34 seeds that he's created, that he's harvested. He eats one, so then he has 33 to plant. So you can see each plant makes 2 seeds for the next year. So the child has to double 33 plus 33, and you can see they're joining 3 10s and 3 10s to get 60, 3 1s and 3 1s to get 6. And the story continues. So Jack now has 66 seeds. He eats one, so he's got 65, which he needs to double. So he plants the 65 seeds. What's the yield of his harvest? Well, you can see here, his yield is 130. Eats one, so now the child has to double 129 and 129. And you can see they're joining their place value position. So 100 and 100, 20 and 20, 9 and 9, and putting that all together. And so on and so on. What's really interesting with this method is children are highly accurate. They rarely make a mistake, but the lines can begin to get confusing. So we do introduce a method where they can work vertically. And at this point, when we're going vertically, we are labeling our ones, tens, and hundreds place to help keep them organized and using grid paper. So when they hit third grade, we want to double check, make sure they've got a reliable method of algorithm that they can compute mentally as well as pencil paper. In this story, the young girl has outsmart the Raja by saying, for my payment, just give me 1 grain of rice and double it every day. And the Raja's like, she's not thinking so well, because just a grain of rice, if I double it, that's 32 grains of rice. That's not very much. But she knows something about the power of doubling, because by day 30, she has, down here, you can see on the recording sheet, a lot of grains of rice. So your child's going to come home and go, Mom, Dad, for my allowance, just give me a cent a day. And just double it every day. Don't do it. We use doubling to develop fraction number sense. These are fourth graders, and again, each of these is an example of a seesaw work done last year. The child has the digits 1 through 9, and we're saying make a 2-digit numerator and 2-digit denominator that is equivalent to 1/2. Now do a 2-digit numerator and a 3-digit denominator equivalent to 1/2. So what I've put in your packet is using all the digits to make a fraction equal to 1/2. And again, children are just applying their knowledge of doubling. Here's one child's solution, but there are many. I hope you have fun with this problem. So this is an assessment, which is more 11/20ths or 13/28ths, and we've purposely put the 13/28ths with larger whole numbers, which ends up being the smaller fraction, because we want to make sure the child understands. And the child says 11/20ths is greater, and here's how she knows. I know 11/20ths is greater because 11/20ths is bigger than 1/2. See, 1/2 is 10/20ths. And 13/20ths is less than 1/2. See, 1/2 would be 14/28ths. You can see that in her markings. And then, of course, we go into complex fractions. So 1/2 is equal to 3.5/7 or 4.5/9. Equivalence is a big idea that we develop in the lower school, and you saw Adiri putting up the second grade equations. This is another second grade's bulletin board. Where it really comes into play is when our second graders learn subtraction with renaming, which is an algorithm you probably learned. And here you can see the child is taking 244 and showing it in base 10 blocks and expanded notation, and then taking one of the tens and decomposing it. So instead of having 40 tens and 4 ones, she has 30 tens and 14 ones. And here's how it translates. When she needs to subtract, do you see the 30 and the 14? Do you see the 3 tens, which is the 30 and the 14? It's just an equivalent form of 244. An equivalent form of 136 is 100 plus 20, 2 tens, plus 16 ones. So this renaming is just putting the number in an equivalent form. It's not magic. Once a child learns that algorithm, they tend to overuse it. So we bring out the remote control and we say, hit the pause button. We really want you to pay attention to the subtraction that you're doing. So pause. Is regrouping needed in this subtraction problem? No, the child says, and they just do column subtraction. Is regrouping needed here? Yes, it is. So the child does regrouping. Is there a faster way here? Could you just count up from 68 to 71? Yes, you could. You can think addition for most subtraction problems. When students in third grade are introduced to multiplication, we start with something called the partial product method. It's very explicit. They see every single step, and the place value is obvious. So 3 times 6 is 18. 3 times 40, not 4. 3 times 40 is 120. 3 times 200 is 60. Again, the students are virtually error-free when they use this method. this came in. I think it's really funny. The child does their multiplication. I switched it around to explain the answer to my grandmother, and I wowed her. Do students learn the standard algorithm for multiplication? Absolutely. In fourth grade, they do. Here we're doing an assessment, asking a fourth grader, how many seconds old are you? So the child writes down her birthday. She's 9 years old. So she multiplies 9 times 365 and figures out how many days old she was on her 9th birthday. But it's been a bunch of days since her 9th birthday. So here you can see she's adding up how many days. It's been 210 days since her last birthday. So she figures out her total numbers of days old, multiplies it by 24 hours in a day, multiplies it by 60 minutes in a day, 60 minutes in an hour, and then 60 seconds in a minute, and decides this number isn't big enough. She wants to calculate her age in nanoseconds, which she does down at the bottom. Again, we want to make sure she has a reliable method of multiplication, which she does. So our instruction is experiential, differentiated, and integrated. We do all of this. The colleagues I work with are really phenomenal. I want to just give you an example of differentiation and lesson integration. Our fourth graders have just completed a multiplication boot camp. And they are just polishing their math facts. This was 3 or 4 days of working on math facts, and as you can imagine, if you had a group of toddlers and you asked the parents when did they learn to speak, there's going to be a 15-month spread. Or when did they learn to walk, there's going to be an 18-month spread. Same thing with memory for multiplication facts. So how do you work with children at multiple levels? You provide multiple opportunities. So a child who needs to work on their times 6, 7s, or 8 facts might be here practicing by factors and doing our packets with riddles and puzzles. A child who just needs to polish their mixed facts might be over here doing number tile puzzles. An example here is this pink one, or playing a multiplication game. They might be making items to help them practice their facts. These foldables or flashcards where they write their strategies, or these multiplication fun facts just to pick a couple facts that they want to polish. What about a student who is already fluent? They're going to still be working on their multiplication facts, but here we've got some application. I'm going to show you 2 of them. And then in terms of electronic tools, I'm not going to show you our practice apps. I'm going to show you something called Texting Story. So first, the Yohaku puzzles. They might pick this packet. And here it says, fill in the blanks of the cells of it. Give the sum or the product shown in each row. So if we look here on the left, this square plus this square must multiply together to give you a product of 12. This times this must equal 18. And oh, by the way, the sum, so we're adding, of these 4 squares must be 19. Over here, you see we're using addition. This plus this is 11. This plus this is 20. And by the way, you may only use the factors of 24. So these are introductory Yohaku puzzles. They get really good. Another puzzle we have are area mazes. These are highly addictive, so I've put a couple for you to try in your packet. All of the values the students need to deduce are whole numbers, but it doesn't mean whole numbers are exclusively used in the puzzles. But wherever you see a question mark, it's going to be a whole number. So you look and you go, how am I going to figure out the length of this side? Well, what do I know? And you start up here in the top, because if the area of this rectangle is 30 inches and one side is 6, then we know the other length has to be 5, because 5 times 6 is 30. If the top is 5, the bottom's 5. So this length here is 8. 8 times what is 56? 8 times 7. So we know that's a 7. Again, we know this has to be 6 because this whole length has to be 8. We know that because of the top and opposite sides of rectangles are equal length. So if this here is a 6, 6 times what is 30? Aha, it's 5. And 5 plus 7 is 12 inches, so we know the length of this side. Anyways, they are really fun. They get quite hard quickly, so I'd love you to try your hand at those. All right, I am going to pull up the texting story so you can see an example of a child creating a dialogue to explain a tricky math fact. All right, this is texting story. Here we go. So if you can put your strategy into words, you absolutely own it. Finally, and really briefly, I just want to show you some content integration. Fourth graders were studying ancient Greece. So we read a book, What's Your Angle, Pythagoras? And students with tiles here literally built Pythagoras' theorem. So they built a 3x3, well, you see the right triangle, so they're learning about properties of right triangles. And this is 3 tiles across, so they built the area, as a squared. So the 9 squares here, and b squared, a 4x4, 16. And they learned that a squared plus b squared is the same as c squared. This 9 plus 16 is 25. And here you can see the child writing out the theorem. And then they're applying this theorem to unknowns. So here they have a right triangle, and they've got one length is 6 and one length is 8. And they have to find the length of the hypotenuse. So they deduce 6 times 6 is 36, 8 times 8 is 64. Together, the square of this c squared is 100, so c must be 10. And then we bump it up, and they have to figure out the length of the hypotenuse here. They know 5 times 5, they know 12 times 12, that makes 169. They're not sure what times what is 169. They start and guess 16 times 16, come up with something a little bit too big. But in doing it, they realize the ones digit times the ones digit is going to have to be 9. So they are pretty sure it's going to be 13 times 13. They come up, they multiply and realize, yes, it is 169. So C must be equal to 113. I do want you to remember this 16 times 16 because they remembered. The next problem they solved had one length as 12. So they knew 12 times 12 is 124, and 16 times 16, they just wrote 256. I said, how'd you know that? And they're like, Ms. Young, we just did that. So again, their memories were good. They added them together, and they got 400, and they knew 400 was 20 times 20. So that's an example of content integration. And I just want to end on this note. Our goal is to develop problem solvers, students who feel they have agency over mathematics. Here they're working on hidden digit problems in 4th grade. They're quite hard. You can see the joy when they finally solve one, and the metacognition, the child able to explain their thinking through a quite charming diagram. All right. Thank you so much for coming. Please get my email down here, eyoung@keyschool.org. Send me your feedback and your questions, and I so look forward to a partnership with you. Thank you.